the depending on the thickness of the polymer or depending on the conditions, the drug will be released. Let us say you need to take 6 or 7 tablets in a full day. So you can take all the tablets at a time, but the tablet will be coated at different thicknesses of polymers such that it will be delivers them. The drug will be released, timely releasing kind of things. And there are a number of biomarker applications are there. Even biomarker. So using gas sensors, different types of biomarker possibilities are there. Recently, I got 2 projects. One is from CERB and CRP. Another one is AICT RPS. These two are the human exhaled gases and absorption as a biomarker. That means a sugar patient will release a lot of acetone in his exhaling gases. So, or before a patient is going to get heart attack, he will release different types of gases when compared to a normal person. So, as a biomarker, even we can use gas sensors as a biomarker. So, molecular tagging, bone growth, dental ceramics, there are n number of applications are there, even in case of biomedical and healthcare. As on today, you know, antibacterial, antiviral, there are n number of things. You also know sunscreen lotions, which are made up of nanoparticles, will have more effectiveness. Why? Because the more surface area will be there, ZNO related sunscreen lotions are available in the market. So fungicides, there are a number of things. Even food and agriculture, people are working very heavily the nano fertilizers. Terry, the government of India is looking, because as on today we are using tons of urea, that means potassium, nitrates, and different things we are using. So people are trying to develop different types of nano pesticides and food packing and also sensors on food packings, especially like we know that very well. On the market there will be some last date for using this food, but sometimes there is a possibility even after last date also food will be very good. So if you can have a sensor where if exactly food is spoiled, like a chicken, mutton, or a bread or a cake, anything, when food is spoiled, then it should change its color. On the strip it should change some color, then you can throw it away. So around 70% of the food we will be wasting because of this last date kind of things. So these are all some of the interesting applications where nano can answer in the industrial. I know a professor in US, where in University of Louisville, where they purchase ZNO Nano in cages from China, which will be $1, and they do some catalytic process such that they increase the surface area of ZNO and they sell it for $16. That means how much difference you can understand. So there will be n number of industrial applications are there. And coming to electronics, I need not talk. There are, you know very well how electronics and fiber optics, lasers brought everything very fast. And similarly, this nano is also going to play a very important role. A new word you could see here, quantum computers. It's an interesting word called quantum computers. The computers, the laptops, whatever we are using are known as classical computers. They work on 0, 1 binary states, like there will be 0, 1, 1, 0, combinations will be there. But if quantum computers comes into reality, then we are going to have 4 states, that is 0, 1, and 0-1 combination, 1-0 combination. That is the interference of 0-1 and 1-0 combination. Possibility is there. It is like a quantum mechanical way of understanding computer science. So people are working on quantum computing very heavily. People are trying to develop different types of gates, NAND gate, NAR gate, kind of things. People are working on this area. If really quantum computer comes into reality, then almost all, like our watch, normal watch can have around 30 to 40 computers, because the RAM size is going to be 10 to the power of minus 23 meters to 10 to the power of 10 to the power of minus 14 to 10 to the power of minus 9 meters. That is because it is like going to be electrons are revolving around the nucleus. So K, L, M, N shells will be there. They are going to be the memory devices. The RAM size is going to be decreased like very heavily, and hence quantum computers is the one area people are working very heavily. So like this, if I am going on talking, there are n number of very interesting applications are available based on nanomaterials. So you may ask, why? What is the advantage of smallness? If I ask you a simple question, if I ask you a very simple question, if you have a sugar powder or sugar cubes, which one will mix very fast? Then you will immediately answer me that sugar powder will mix very fast. Why? What is the reason? The reason is very simple. When it is small, it is more reactive. Smaller can become more reactive. This is very simple, fundamental thing you can understand. Like as a very normal way, every day in the life we will be doing. If you have given sugar powder and sugar cube, generally you know very well sugar powder will mix very faster, and hence the basic reason is small becomes more reactive. Then immediately you should also ask another question, because I was talking about nano. How small is going to be more active? Is it milli size is going to be more active, or micro size is going to be more active, or nano size is going to be more active? If that is the case, milli is 10 to the power of minus 3, micro is 10 to the power of minus 6, nano is 10 to the power of minus 9 meters. Why we did not study the milli technology and micro technology, and why directly we jumped into the nanotechnology need to be understood very clearly. So here the smallness will change different things. Let us take gold. The gold color is going to become red. Not only red, it can become brick red, blue, and then light blue color, and then yellow, and then like water. So when you reduce the size of the gold, the color of the gold is going to be changed to different colors. That means the physical properties of the materials are going to be modified when you reduce the size of the material. What happens in the case of milli and micro, we need to understand. And then melting point is going to be modified. The strength of the material is going to be changed. Conductivity, that means the resistivity or conductivity of the material is going to be modified. Reactivity. These are all the fundamental phenomena, the fundamental properties of the materials are going to be modified. Here, I want to talk some 2-3 minutes. Please try to understand the concepts here. I don't have a separate PPTs for this, but however, so the color of the material is going to be modified in case of gold. And that is the reason, as on today, people are using gold dots as imaging agents in cancer treatment, cancer therapy, not only therapy in the form of therapeutics. What I mean to say therapeutics is something like as a simple logic, especially in case of cancer. If a patient get cancer, you know very well, there will be different areas, people will get lumps will be formed. This is known the primary lump and secondary lumps, and like that people will form. So how it is going to happen is there will be CXCR4, let us say in case of, especially in case of some lumps, some CXCR4 and CXCL12, these two will combine and they form in the form of a lump. So positive and negative will flow in the blood, and slowly they go and they go at the lymph nodes and they try to form a case of form in the form of a lumps. So in the case of generally the treatment, whatever we do here is we have a PET scan where you could see the lump immediately. But after that lump, no one knows where the secondary lump is going to be formed. So we need to track it, how it is going to be formed, the second lump. Like let us say CXCL12 is then, I have to create CXCR4 by using gold nanoparticles and some polymers, and you have to lock it somewhere such that the secondary lump will not form in the blood flow process actually. So kind of imaging, and people are using even gold in Ayurveda, basmas. People, lot of in our tradition also, people will use a lot of gold. We know very well as well. If you see in olden days, people used to eat in silver plates, which in the middle of the silver plate there will be a gold flower will be there. If you see in olden days, old people, very rich people used to have such kind of things. Why? Because when we are putting hot rice there, a little bit of gold is or silver is going inside the body, and you know very well, gold and silver are antibacterial very well. And even we start our babies feeding in the beginning, like after 6 months, we start feeding our babies. They are also silver cup and silver spoon. Sometimes we may not clean it very properly. In spite, bacteria will not grow and children will not get any health diseases kind of things. There are n number of things are there like such that. So not only this, there will be a possibility of, there will be a magnetic properties. Magnetic properties will be modified, and then conductivity. If I say conductivity, electrical properties of the materials will be modified, and strength, the mechanical properties, because of different strain in the materials and different domains, materials domains will be modified. Because of that, strength could be modified, increased or decreased, and temperature. These are all the some of the optical properties. This is best example for an optical property. Due to the plasmon resonance phenomena, this type of color changes will happen in case of gold and CDS nanoparticles, and there are different other nanoparticles are there. So these are all the, so what I mean to say here, when you are trying to reduce the size of the materials, their properties are going to be modified. Fundamentally, we need to maybe magnetic properties, maybe optical properties, maybe physical properties, maybe electrical properties may be modified. Based on that, we need to understand even thermal properties. As on today, you know very well, different types of engine oils will be used in missions. So if you can control the specific heat of that particular liquid, the meaning of that is how fast the temperature increasing, or how fast it is cooling, or how fast it is heating. If you can control, then automobile things will be modified a lot. So specifically, if you can design some oil such that even after a lot of journey, if it is not increasing its temperature, that means if you can control the specific heat of that particular liquid, you can control how fast it is increasing temperature and how fast it is cooling its temperature. So these are all the fundamentally you can modify some of the physical things, thermal things, optical things, magnetic things, and then you can use it for different types of applications. This is what is the smallness is going to lead. Then why it is happening? when it is becoming small, what is exactly is happening, we need to understand. So let me take a very simple example and try to work it out. Consider a 100 nanometer sphere, a 100 nanometer sphere. Even you can consider a 100 meter sphere. Now, similarly, take a paper, and if you have a pen, you can calculate it. So now what I am trying to compare is, let us take 100 meters and 100 nanometers sphere and try to find out its volume and its surface area. What is the formula for volume? We know very well, 4 by 3 pi r cube. What is the surface area formula? 4 pi r square. So as I told, diameter d 100 nanometer. I am calculating it for 100 nanometers. Try to calculate, you all people, if you have a pen and paper with you, for 100 meters. So what happens? Pi into 100 into I converted into meters, 10 to the power of, because it is nanometers, 10 to the power of minus 9 whole cube. That is, the volume is going to be 5 into 5.24 into 10 to the power of minus 23. This you see. And similarly, I also calculated surface area formula. So surface area is nothing but, so 10 into some, so 3.141 into 10 to the power of minus 14. Now, I am going to find out, you please also calculate volume and surface area and try to determine surface to volume ratio. Surface to volume ratio. That means surface to volume ratio. If you calculate that, you wonder, when you are calculating surface area to volume ratio, what happens? Surface area will be 10 to the power of minus 14 and volume below will be 10 to the power of minus 23. And it will become 10 to the power of plus 7 on an average. Am I right? Am I right or not? This value you are going to get more than 10 to the power of 7. Whereas in your case, what might have happened, because here there won't be this number and this number, you don't get approximately surface to volume ratio will not be this much high. Greater than, here in this case, it is greater than 10 to the power of 7. This gives an approximate surface to volume ratio, which is significantly larger than micro-sized particles. You might have understood, when you calculate in case of 100 meters, you will see a very different scenario. Whereas in this particular case, in the case of nano, it is going to be surface to volume ratio is going to be increased enormously, predominantly. As the surface to volume ratio is increases, the percentage of atoms at the surface and surface forces becomes more dominant. This is another interesting point we need to understand. As the surface area to volume ratio is increases, please, this is the first takeaway of you people. Please try to understand here. So what I told you very clearly, when you are reducing the size, there may be a change of color, melting, strength, conductance, reactivity, magnetic properties, electrical properties, mechanical properties. All these are going to be changed. Why they are changing, you need to fundamentally understand. Once if you want to understand fundamentally, then I took a simple basic example that 100 diameter nanometer and 100 nanometer and 100 nanometer. So I tried to calculate volume, and I also tried to calculate surface area. And as volume is below it is going to be 10 to the power of minus 22, automatically the surface to volume ratio is increasing enormously. This calculation is going to tell us that as the percentage of atoms at the surface and surface forces becomes more dominant when you reduce the size of the atom, size of the material. Whereas in case of bulk, it is not going to happen. Generally accepted material properties are derived from bulk, where the percentage of atoms at the surface is minimum. This property changes the nanoscale. This is the first property you need to understand. I think you please have a reflection here. You please try to think yourself, when you take any example, take a cube, take a volume, and try to calculate in the range of nano and in the range of meters. You will find surely there is surface to volume ratio modification. Surface to volume ratio increase will be heavily will be there in case of nano. That is the first fundamental point you need to clearly understand. Another simple example, let me take another simple example. Take a cube whose diameter, length 1 centimeter, width 1 centimeter, height 1 centimeter. And calculate once again. Now we will calculate in a different way. I am going to cut it into pieces. First piece, and then surface to volume, surface area I am calculating. What is the formula for surface area? 6 into length into breadth. Am I right? Length into breadth. So if you calculate this, so I'm going on cutting into pieces. So if I cover this material, I can cover a full football ground. Which football ground is around 2 point, it will be like on an average more than 8 hectares, I think. General internationally, if you consider a football ground. So what I mean to say here, so when one cube, I'm going cutting pieces, cubes, I'm going cutting, and I'm trying to calculate the surface area of total pieces. Then it is going to cover. So what I mean to say here is, the basic point is, when you are trying to reduce the size of the material, its surface to volume ratio is going to be increased predominantly. That is the basic point I want to tell you here. That is the point clearly you need to understand, sir. You need to understand here. If you understood this point, this is the key role of understanding nanomaterials or nanotechnology. So I repeat once again here very clearly, when you reduce the size of the material, its surface to volume ratio is predominantly increasing. This makes the material's properties something different. Based on that property studies, we need to understand here. But however, if you want to clearly understand about the nanoscience or nanotechnology, you need to know interface concepts, quantum confinement, thermal fluctuations, discreteness of matter, and all these things. But don't worry about all these things as of now. But from these quantum effects, I will try to take a graph. The graph is basically drawn based on quantum mechanical understanding here. Try to concentrate on this graph very clearly. This is going to be the second takeaway. The first takeaway, what I told till now is, when you reduce the size of the materials, its surface to volume ratio is going to be increased enormously. And the second point, what I am trying to tell you here is, I am reducing the size of the materials, and I am taking on x-axis the size of the materials. 10 to the power of minus 9 nanometers, 10 to the power of 8 nanometers, 10 to the power of 7. This is in nanometer scale. This is in nanometer scale. And this is surface to volume ratio. A by V. A is surface area, V is volume. So when it is 1 into 10 to the power of minus 9 meters, sorry, 1 into 10 to the power of minus 9 meter, it is on the x-axis. So it is on x-axis. What is this point? It is 10 to the power of 6 nanometers. That is nothing but 10 to the power of minus 3 millimeters. This is 1 meter, let us say. Am I right? And this is 10 to the power of minus 3 millimeters. And Even even size is reducing, but surface to volume ratio is 0 only. It is the same. I am coming here. What is this? It is micro. Micro means 10 to the power of minus 6 meters. That is opposite to mega. Micro, 10 to the power of minus 6. Here also nothing is happening. But what is this? It is 100 nanometers. At 100 nanometers, after 100 nanometers, in this region, after 100 nanometers, something interesting phenomena is happening. What is that? There is a increase in the surface to volume ratio. Are you following it very clearly? Till at 1 meter, nothing happened. At 1 millimeter, nothing happened. At 1 micrometer, nothing happened. But at 100 nanometers, interesting phenomena is happening. That means below 100 nanometers, something is happening. That is the reason why nanoscience, people are talking. The basic definition is, if the material size is below 100 nanometers in any dimension, let us say three-dimensional material is there, in any one dimension, its size is in nano, then we can say that is nanomaterials, like carbon nanotubes. The carbon nanotubes, the diameter is in the nano, but it may be 1 meter, it may be 5 centimeters, it may be 4 centimeters, even that is called as a nanomaterial. So what I mean to say here is very clearly, in the case of milli and in the case of micro, there may be some size effects, but not nano effects. There is no surface to volume ratio modification is happening. But below 100 nanometers, this particular phenomena, the surface to volume ratio modification is happening. And because of that, the materials are behaving very differently. And because of that, they are going to have different fundamental properties are going to be modified. As you know very well, the color of gold, but when you reduce the size of the color to 50 nanometer, it is going to be brick red. And if you are making it to 2030, then it is going to be blue in color. So if you are going to make it 4 or 5 nanometer, it looks like a water. So what I mean to say here is, in the case of gold, the optical properties are going to be modified. In some materials, the mechanical properties may modify. In some materials, the thermal properties may modify. In some materials, magnetic properties may modify. So you need to tap corresponding to your application, and you need to use it for your application. This is what is the fundamental difference between the bulk materials and nanomaterials. So till now, I gave 2 takeaways, 2 points to all the participants. The first takeaway is, surface to volume ratio modification is something different in case of nanomaterials when compared to the bulk. And the second question is, even milli is small, micro is also small, and why we did not study milli and micro technology? The reason is here. The reason is here. At 1 meter, at 1 millimeter, at 1 micrometer, nothing is happening. But after 100 nanometer, something interesting phenomena is happening. This phenomena is nano. This area is nano region, and the definition is this. Based on this, the definition is defined. However, don't worry about this particular point. But when you in the case of quantum mechanical way of understanding, people know the word Schrodinger's wave equation. Based on the Schrodinger's wave equation, you can design Hamiltonian for any type of material. So if you design energy levels for bulk materials, it will be like this. For large nanoparticles, it will be like this. For small nanoparticles, it will be like this. So what I mean to say here is, the energy levels are distinct, and different energy levels will be there in case of nanomaterials. Whereas in case of bulk and large particles, the energy levels are different kind of things. But don't worry, try to understand, don't worry about to understand this concept. For the sake of completion,
Hello, sir. Sir, hello. I think some problem from sir's side.
I'm like, okay. Hello, are you able to listen me? If
Yes, sir.
someone says, yeah, thank you. There is a current problem. I connected with another internet. I don't know how far it will come. I'll try to see. In the meantime, current will come. However, don't worry. I'm sorry for the inconvenience. Yeah. So till now, I was trying to tell you all that the two takeaways, 2 points only I was trying to discuss till now. The first point is uh, uh, nano and nano materials, why they are different when compared to the normal material. That is the one point I was trying to tell you. And the second point is why only nano, why not milli and micro? That is another point I was trying to discuss till now. And however, from my talk, from my words, you might have understood that nano is not at all a new kind of word, because even our homeopathy, basmas people were using, even our grandmothers know how to prepare not exactly carbon nanotubes, but carbon materials, maybe in the size of micro and nano. The causal which they prepare for eye, we will keep a black thing where they use some combustion phenomena, where they use some oil and then other things. From there, they develop different types of materials. Even such kind of a simple example, even silver nano kind of things. As on today, we know very well that antibacterial cloths, antibacterial undergarments, antibacterial towels are coming. Because they just coat some of the nano materials there, so simply silver kind of things, where bacteria will not grow kind of things. So basic point, what I want to tell you that nano is not at all new. But you may ask why this much time we took to understand nano kind of things. The simple thing is nature. From nature, we have to understand everything. Because as on today, we got different types of microscopies like electron microscopy, transmission electron microscopy, scanning electron microscopies, where electron optics came into reality. You know very well, earlier we used to have optics, optical microscopes, where you could see micrometers only, in the range of micrometers only. But when TEM, SEM, transmission electron microscopy, scanning electron microscopy, atomic force microscopies made us to see atom by atom and molecule by molecule. Somewhere this is a triggering point to this type of nanomaterials, to see morphologies and to see individual atoms and to understand the science more effectively. So let me take you to the nature, simple example nature, like a peacock feather. You see peacock feathers, you whenever you see peacock feathers, we feel really very happy. Why? Because the colors are bright, and in the sunlight it will have a different types of colors, and color modification, like different colors we could see, different colors, and no one is cleaning them. The beauty is they are self-cleaning. They look always bright in color. They look, when sunlight falls on it in a different shades, you could see very clearly. And why they are so colorful, and why they are so bright in nature, what made them bright in nature. So basic science, whatever we have, can be explained due to the surface smoothness, or due to the surface tension effects, and due to the contact angle kind of concepts we could explain. But now I am trying to take you people to zoom it, zoom it, and zoom it, and zoom it. So when I am zooming the peacock feather to micrometers, and then micrometers, and then some more small. On this, once again, I am zooming it. You see a fantastic nano size holes repeated as a pattern in the nanoscale. See here, small holes, small holes. These are all small holes which are there on the peacock feathers when I zoom it and zoom it and zoom it to 500 nanometers, below 500 nanometers scale. So what I mean to say here is, whatever you are seeing this and whatever the science and technology you could explain. But if you go on, zoom it and zoom it and zoom it, and you see the reality. If you more zoom it, I don't know what you will see. But in the range of 500 nanometers, you could see a nanoscale pattern reflects light on the create irradiance, different colors. So my question is, if you can mimic this kind of material, it is possible to develop this kind of colors, this kind of bright colors, this kind of bright watches, this kind of bright cars, this kind of bright cell phones. No, you name it, anything, or you can color, you can develop some paints. When sunlight is there, house looks in a different color. When sunset is there, house look in another color. So even our dress, when you go to the college morning, 10 o'clock, it will look in a different color. After sun, kind of some other color. And after evening, when you are coming home, it will be in a different color. Can you imagine this kind of interesting phenomena, like a peacock feather? And the beauty is you need not wash it. This is very interesting phenomena actually. Washing clothes is a tough task actually. And nowadays, very well, a lot of rains are coming. Washing clothes is only one topic, but how to dry them, it's another big topic actually. Very well, there is a lot of science once again. Why the cloths are drying basically. Water will evaporate at 100 degrees centigrade. And what phenomena is happening at room temperature, water is going away from the cloth. If you think that also, it's a big science once again. You need to understand in a very different way how water is going away from the cloth, even at some particular below, it's like, see, at 100 degrees centigrade only water will evaporate, very well. And the time and the weather and what phenomena is happening to go down, the cloth is becoming wet to dry. It's a different, once again, a different kind of science. So what I mean to say here is, understanding the nature itself is technology, itself is science, itself is innovation. People think that if they want to do research, if they want to write papers, big papers, they need very big labs, and they need high-end instruments, and they need a lot of equipments, and they need a lot of data. If that is the case, Raman simply was traveling in a boat where he was trying to understand how light is scattering on a particular drop of water, and he invented a phenomenal effect, Raman effect. As on today, Raman effect is the one of the great work. It's as on today, people are developing Raman effect, and people are trying to understand, or based on Raman effect, surface enhanced Raman spectroscopy. Where I did my postdoctoral research in John Hopkins, I worked on surface enhanced Raman spectroscopy for imaging of cancer cells. So what I mean to say here, have nature, being a scientist, being an engineer, we need to develop our students as well. We need to have that eye of nature, nature sensitivity. Nature sensitivity makes a lot of innovations. You also know very well, only one boy came and told that apple is falling due to gravity. Before also gravity is there, after that also gravity is there, but he could derive capital G and small g, universal gravitational constant formula, and all other things. Why? Because he saw that why apple is falling. This is all simple things I just want to mention you. So it may be nanotechnology, it may be whatever, it may be science or engineering, whatever you are developing. This is all basically a way of understanding nature. If you understand nature, nature will that itself is a science, basically. That is what I feel. So if you see the peacock feathers, different colors, everything is in a different color. Why this color is coming? Why is that actually? If you know that, then you can create different things, different colors. So same, if I zoom it, then a ribs of like a chip ribs are coming up. So if you can design this kind of things, this material will give you an interesting kind of applications and interesting phenomena. You need not have a separate card like what is that? Credit card, debit card, identity card, Aadhaar card, kind of things. One card will talk everything. Kind of this kind of mimicking, biomimicking, all these things. For only one person, it will work. For unique identity kind of things are possible with this type of biomimicking. Another very simple example I want to give you: butterfly. Lotus leaf. If you take lotus leaf, you know very well water will not touch it. Why? So I once again zoomed it. You see, these are all nano rods, maybe micro rods. What happened here? Because of this thing and surface tension and hydrophobic nature of that particular liquid. So now you can design a number of same principle. You can use it like anti-fogging glosses in bathrooms or for cars, or you can develop a number of things based on this kind of equipment, with this kind of fundamental phenomena. Even Spider-Man, Superman, all these things also, I can say, if you can zoom it, and zoom it, you see very interesting phenomena. So what I mean to say, in nature, everything, if you go down to small, like zoom it and zoom it, everything is nano. So what I basically mean to say, everywhere nano is there. It is not a new kind of technology, and suddenly it did not came into the field. It's everywhere, and we need to have a look of understanding. So basically, what I mean to say, whatever thing from nature, people are trying to understand, and understand. This is what is the basic point. The third takeaway is whatever research you are doing, whatever development you are doing, basically have a sensitivity towards the nature. So that will give you a clarity what to do and what not to do. And coming to sensors. Once again, when I come to sensors, taste, hearing, seeing, smelling, touching, all these are sensors. You know very well. But the problem is, I can't say how cold it is, how hot it is, or I can't say how sweet it is. Means I can say more sweet or less sweet. I can't say a number. I can't say smell. I can't say kind of things. So here, that is where sensor is coming. That means hearing. If I say 100 decibels of sound is coming, 70 decibels sound is coming, kind of thing, then the instrument will tell that. That is called sensor for hearing. Or you know very well, simple sensor, we know very well from our childhood days, temperature sensor, thermometer. Basically, what is the fundamental principle? There will be some alcohol or mercury will be there inside. Nowadays, people are using alcohol or mercury, different things are there. So when you when alcohol, mercury is given some temperature, its volume increases. Based on the volume, temperature is noted down, and based on that we could say normalize it. Basically, this is what is a simple example. In olden days, people for generally tests, analytical tests used to be taken in laboratories, but as on today, every Friday and Saturday, you could see sensors used by police people in normal life, normal today life, like alcohol breath analyzer. So you know, very lot of jokes and lot of things will be happening in or around our place only. So this is one best example of gas sensor. It's a breath analyzer, alcohol breath analyzer, basically. So these are all some of the examples, and the sensors can be used in environmental monitoring, like in water, like even you can keep some sensors in water. If some problem is there, some levels of pollution is increasing, it will give us even in medical diagnostic systems. That means continuous monitoring of a patient. If you want to monitor continuously, let us say as on today, the problem is sugar patients, so they need to always go to the some test center, and they need to prick, and they need to take the blood, and they need to say before food, after food, and after 1 hour food, kind of things. They always prick and they take the blood, and they will calculate the blood, how much sugar is there in the blood. So if you have a continuous monitoring system like this, where it is directly attached to the system, disease possibility are there. In automobile engineering, there is once again vast applications are there, like manless car. I have a video, I will show it to you. And then manufacturing system, defense is one area where sensors are used very vastly. Space, in home as on today, like fire alarms are there, and security alarms are there, n number of alarms people are using. So this is one where n number of things. So let me play this video. Are you able to see this video? Sorry, Sorry, I just want to make it little fast and so basically, what I want to say here is almost all the sensors were used in a car. Manless, I'm not I'm not promoting any company or anything. Here, I just want to tell you that there are n number of sensors are there. If you consider a luxury driverless cars embedded with different types of sensors, starting from ending, every lot of sensors are possibilities are there. So what I mean to say, there are n number of, as on today also, light switches, refrigerators, climate control appliances and toasters. Even in our toasters also, there are temperature controllers are there. So now I'll be just trying to give you, till now I talked about a sensor basically. Especially, I want to take you the next 20 minutes journey is a kind of my research. So before I am going to my research, here I want to tell you 3 points. The first point is I try to give the concept of sensor, and the next point what I am going to talk is what are the different types of gas sensors, and after that I'm going to talk especially about our research chemoresistive gas sensors and their applications. This is the next 25 minutes, around 25 minutes I'll be talking. A sensor is a converter that measures the physical quantity and converts it into signal. See, even our eyes are sensors, our ears are sensor, but we can't tell you exactly. We cannot give you a signal, exact signal kind of thing. So this is what is a specialist sensor. In the sensors, you can use mechanical energy or electrical energy. These are the two possibilities are there, like velocity, acceleration, force, pressure, temperature. These are all the some of the quantities we will use. Otherwise, in the case of electrical, current, voltage, capacitance, inductance, and even resistance. Inductance means automatically in a circuit resistance. So a sensor requires a physical parameter and converts it into optical or electrical or mechanical signals which are suitable for processing. We need to process them actually. So based on the processing, we can have these many types of phenomena actually. So coming to I am now working on, sorry to interrupt you, I am working on a separate current system. Current till now did not came. I don't know when it will go. Now, as of now, I am managing it. I'm sorry for the inconvenience for the people, but now I'm going on. I think 20 more minutes it will be available. So basically, a sensor is a technology device that detects or sends signal, physical condition or chemical compounds. Let us say it's a transducer. As in the case of alcohol breath analyzer, he is using the gas alcohol, and here some element will be there that detects this, and the transducer will be there, and it will be some integrated circuit will be there. From there you will get some signal. Signal is nothing but a number, digital number. So below this number he did not have alcohol, above this number he consumed alcohol. Kind of things will be understood based on this kind of basic circuits. As on today, there are n number of sensors are there, like ultrasonic sensor, gas sensor, color sensor. And you may ask, sir, why are you working on gas sensors? So I worked on gas sensor, especially on LPG gas sensors in home holes. They are there, but they work at 150 degrees centigrade. What I mean to say, so we need to connect it always to a current, and the element should be heated till 150 degrees centigrade. Then only when gas comes, it will detect and it will give alarm. So we will be trying to work for 50 to 60 degrees centigrade LPG sensors. That is the beauty in our research actually. So in olden days, people used to have birds or some kind of lamps to go to inside the different the Singareni things where people go in mines. They go inside the mines. They used to take this kind of lamps where if lamp is gone after some time, people know that there is no sufficient oxygen and they come back. Similarly, if bird is not coming back, they assume that some gas problem, some kind of oxygen content is not there. If it is there, so people used to do like earlier, it is the concept. But now there are a number of applications are there. So now what I told you, I was trying to tell you that I am working on gas sensors. But what type of gas sensors? It's a simple mechanism. I will be measuring here. I told you in the beginning, here we can measure current, we can measure voltage, we can measure capacitance, we can measure inductance, even we can measure the resistance. So here I am measuring the resistance in my case. What happens? The fundamental way of understanding of a gas sensor is a very simple thing. So there are two possibilities are there. One is N-type, another one is P-type of material are there. But don't worry about that. So when a material is there, when gas comes to this material, what are the possibilities? One is oxidization, other one is reduction. Oxidization, reduction. That means giving electrons or taking electrons. These are the two phenomena or possibilities there. When gas comes to the material, there is a two phenomena possibility. One is gas may oxidize or it may reduce. These are the two phenomena are there. But once again, basing on the type of the material. So these are some examples of reducing gases like N3, H2S, CO, H2, CH4. These are all reducing gases. These are all oxidizing gases like O2, O3, and OX, Cl. There are different types of N type of materials and P type of materials. Sorry. N type of material and P type of material. So when you are giving these materials, so when gas comes here and it may oxidize and it may reduce depending on that. Let us assume that you have a multimeter with you in the probe of resistance. If you keep the resistance, then you can measure the resistance. Simple logic is that. That is what is this measuring mechanism. So what are the parameters? Very important parameters of sensing, like chemical composition, crystallographic structure, catalytic activity, surface structure, and morphology. We play morely on this type of materials because we are working on nanomaterials. We develop different types of nanomaterials like rods, like flowers, like shapes, different plate shape, different type of materials, and based on that particular materials, we will be having a chemical composition of the material is very important, crystallographic structure, catalytic activity, surface structure, and parameters of the sensing elements are thermal stability. This is very important. Like with temperature, how it is going to vary, the selectivity of the response, selectivity of gas response. What I mean to say, I designed alcohol breath analyzer, but you took coffee, and for that also it gave a sensing. Then what is it a perfect alcohol sensor? No, it is not it should only give response to only alcohol, not for coffee or tea or a cool drink. So that is the difference. Sensitivity is a very important parameter, gas sensitivity. How much you took a lot of alcohol, you took less alcohol. There should be a comparison should be there. How much is sensitivity? And better is room temperature, operating temperature. If it is not room temperature, we need to connect it to power supply separately, or we need to use the battery. Rate of response, that means after keeping a person's mouth, I have to keep for half an hour. Is it a good response time? No, within 1 minute or 30 seconds or 40 seconds, if it gives the results, then we say it is a good instrument. So response time should be less. Operating temperature should be room temperature. Sensitivity should be very good. Selectivity should be very good. Then we will say it is a very good sensor. And coming to the graphs, which I will be talking, however, I will be talking in the next area. But however, listen here, this is the time and this is the resistance. I am measuring with respect to time resistance. So what I am doing, I am keeping nanomaterial here, I am sending the gas here, and I am connected a multimeter here, and I am measuring the resistivity, how the resistivity is going. So what happens when gas is coming, resistivity may increase or may decrease if it is an N-type or P-type of material, or it is oxidizing gas or reducing gas, depending on that. So first, gas is coming, and then here in this case, resistivity may decrease or may increase. This particular time, the saturation time, is known as response time. After that, there will be a saturation, and then we should come to normal position within recovery time. So response and recovery time should be very, very small. Then only we will say it is a good sensor. These are all some of the physical things and parameters of materials and parameters of the sensing element we need to understand. So the same graph, I told you, selectivity, sensitivity. Gas sensitivity formula is nothing but resistance in air by resistance minus resistance in gas divided by resistance in, it is a percentage basically. Response time, recovery time, long stability. These are all some of the very important parameters of any gas sensor. So a simple example, what I'm trying to give you. This is the circuit diagram, what I'm trying to tell you. So this is a sensing probe and gas is coming here, and I connected, I told you, I want to measure resistance. When I am measuring resistance, it is called chemoresistive gas sensing. If I measure current, then I will say amperometric resistance. If I am measuring voltage, then I'll say potentiometric gas sensing. So you understood the mechanism, the physical, the phenomena what I am using. Here I am using resistance. So at constant voltage, I am measuring resistance, and hence I will say it is a chemoresistive gas sensing. If I am not using current, so it's all depending on how you design your sensor, how you develop your sensor it's all your interest. So I told you these are oxidizing, reducing gases, N-type, P-type materials, the formula for sensitivity, and so when gas comes here and it will absorb all the it may oxidize or it may reduce. Depending on that, I will be measuring resistance. There are 4 possibilities are there. One is if N-type material and gas is reducing, then what happens? Conductivity increases. That means resistivity decreases. If it is oxidizing gas and N-type material, conductivity decreases. That means resistance increases. If I am talking reducing gas and P-type material, then resistance increases, conductivity decreases. These are the 4 possibilities are there. However, you may get graph like this or like this. These are the 2 possibilities are there. So this is how you will work. So if you want to say a very good sensor, if you want to design a very good sensor, then accuracy, response time, specific, good sensitivity, low operating temperature, size of sensor should be small, maintenance cost should be small, reliability, durability, and eco-friendly. These are all some of the qualities. So here I'll be talking about this particular work. Why I selected this case work is, this is an MTech student work. It is not even PhD student work. It is an MTech student work who published 4 papers actually. So basically we use different types of synthesis methods. We do synthesis, characterization, property, and application. So this is the sensing setup which we developed in our lab, which is around 46 lakhs. I got a project in SERB. Recently also I got another project SERB based on this only, like last 1 month. So here this is a very simple thing. So this is the chamber where we will keep the nanomaterials. Nanomaterials means these are the elements: aluminum electrode, gold electrodes, flexible electrodes are there because we want to study even on the flexible electrodes. We coat our nanomaterials here or here. This is the nanomaterial. So these are the connections. We will connect it here. We will put this material here, and these are the cylinders, zero gas and analyte gas, whatever gas. And because we are using LPG, we developed our own setup actually to measure how much LPG is going. This is a computer. This is a cathelimeter, which can measure 10 to the power of minus 6 ohms difference also. If you have a multimeter, the sensitivity will be very small. So I have a cathelimeter where I can measure 10 to the power of minus 6 ohms difference also. Micro ohms difference also I can measure. This is a vacuum pump. After keeping this material, I will suck out all the gases which are there, and then I will send analyte zero gas. That means everything will clear, and then I will send out my particular gas, and correspondingly I have a 4-probe setup, resistivity measurement, 4-probe setup, where I will measure the resistivity in the circuit, and from there I will calculate all these things. So don't worry about this is a graphical abstract. So we synthesize the material, and we add this material to these IEDs, and we connect it in the setup, and LPG will come, and then we will measure the resistivity based on that. So here, an interesting method, a simple chemical method we did, hydrothermal template method. So we took egg shell, and from that shell we took this thing, and basically we used egg membrane we used as a membrane shell, and this is the same image of egg membrane shell, and we developed a simple technique methods will be there, and we developed this synthesis, and after synthesizing this nanomaterial, we do different type of characterization techniques. So X-ray diffraction is for structurally measurement. That means, let us say NaCl. If I say NaCl, it should have proper peaks. This peak, yeah, based on Miller indices, we can internationally we can say that SMO2 is prepared, and this is an FTIR where we can see the structure based on length, bond lengths. We can measure the structure, and then UV optical properties, and then purity. To measure the purity, we did SEM, ADAX and SEM, where you could see it's like rice-like structure, flower-like structure, all this same material with different temperatures and with the small modifications. See, you can see long rods, small rods, flower kind of thing, hierarchical structures. These are also hierarchical structures. These are like rice kind of structure. There are different types of structures we prepare, and then we coat this nanomaterial on this particular electrodes, IEDs. It's interdissociated electrodes, which we need to purchase, and then we coat this nanomaterial there, and then we connect it in the circuit. Once we connect in the circuit, we will get the graph. So we will set the voltage, and we will set the particular gas current gases to be sending, basically LPG gases. There will be gas mixture will be there, and then based on that, we will, after this characterization, first what we did, LPG concentration and response, how it is getting. And this is a big study actually. After this, we will time versus resistance, like the graphs, whatever we are getting. And see, this is the response time, and this is the recovery time, and this is what is the basic thing. If you modify it, you will get it like this. And these are the selectivity, how response is there. Like if I am sending LPG, this much of response is there about, and when I send CO2, Ni2, acetone, ethanol, there is a less response is there. So I feel that this is very good for this type of material. And even what we did is we bent the electrodes. That means like in cloth, some people may want to use in cloth, or some people may want to use in somewhere where it need to be bent. Even that, the results are perfectly matching. This is one example in calculation. I assume it's 11:20, and some more work is there. I don't want to go and tell you all these things. Here I will just go to even sensors will not be sufficient for me. University of, I work in, you know very well, I work in Institute of Science and Technology, and Institute of Science and Technology has got different centers. I work in Center for Nanoscience and Technology. We run MTech in nanotechnology and PhD in nanotechnology. At our center, we work in different areas like energy, battery, solar cells, agriculture. Agriculture means like seed germination, and then we also work antibacterial activity, antiviral activity, anti-cancer activity. Our basic work is sensors and biosensors, like we work on glucose, gas, humidity sensing. Even we work on water purification, especially some of the components we can remove based on absorption phenomena. And these are some of the facilities which we have at our Center for Nanoscience and Technology, TGDTA, atomic force microscopy, X-ray diffraction. Raman is not working as of now. UV spectrometer, ball milling, spin coating, thin films. There are different types of thin film setups are there, like spray pyrolysis, RF sputtering, magnetron sputtering, normal things, dip coating, and then ball milling, nanoparticle size analyzer, chemical vapor deposit, CV, and cyclic voltammetry, solar simulator, and then incubator, DNS, nanofluid ultra. This we work on mechanical properties of the nano materials, contact angle emission, hydrophobic and hydrophilic nature of the materials, and FGIR. These are all some of our instruments. These are all some of our old students who completed their PhDs, and there are 14 PhDs completed, and as of now, 6 PhDs are working in different areas. Thank you very much. The session is open for questions.
Thank you, sir.
Thank you very much for the opportunity. The session is open for questions.
Any doubts, you can ask, sir.
If I'll try to answer. If anything is there in message, just I can also answer. I want to tell you one thing. Generally, questions are there won't be, questions will not be evaluated anyhow. Questions are questions, only answers will be evaluated. So all the questions are correct. So you can ask any question. Or any interaction.
Somebody posted in chat box, what is integrated molecular manufacturing?
I did not understand the question.
One more.
How was nano? Yeah. This Madan Mohan, can you, if you talk, it will be good actually. I did not understood the question what you are asking. And coming to Sarath Babu.
Sir, actually, for that, yes, am I audible? This is Madan Mohan speaking.
Yes,
here.
you are audible.
Sir, according to the developing of the molecular manufacturing, there are certain points that I have to understand. One is from the basic molecular manufacturing, another one is exponential. And I can understand the exponential, the ability to use something manufacturing system to build certain additional useful molecular manufacturing system. But it can possible to produce large quantities of the product related to the exponential. But what my point is, what do you mean by the integrated molecular manufacturing? Is there any integrated molecular manufacturing in this, the bio nanotechnology, whatever?
Yeah. Yes. But the main problem is reproduction. Reproductivity is one of the tough tasks. Actually, all these when you come to nano levels, the main drawback as of now people are facing is chemical engineering, the process engineering. The process engineering need to be understood in a very effective manner. It is in the beginning stage. Once if you, let me put it like this. I can prepare the same material with 1 gram or 2 grams or 3 grams, but I cannot prepare the same material in 1 kg with the same morphology, with the same phenomena. This is what is the problem. Upgrading the things, upgrading whatever things, if you are producing in grams, you could not produce in kgs. That is what the big problem in nano as of now. What I understood actually. Madan
Okay.
Mohan, I'm exactly not a molecular manufacturing person, but I whatever the
Okay.
uh, basic question from you, I understood that, and I try to answer.
No, actually, my
Is it
doubt is that is there any ability to combine whatever the output of this molecule manufacturing that can converting into the lot product?
Yes, that is the process engineering. That
Okay.
is the big task actually. As that is why people are unable to market, or people are unable to produce the nano things in a better way. The basic problem is process engineering is going to be a tough task. Need to be understood. There are a lot of questions which we need to understand in process engineering actually. That is what is the answer I can give, Madan Mohan Garu, as of now.
Okay, sir. I got it. Thank you very much.
Thank you. And one more question: how to coat the materials on the like sensors? One question was asked, and it is called. There are different methods. Are there? We do dip coating, and we do a number of, depending on the type of the material and depending on the type of the IED, interdissociated electrode. We have to set that kind of thing actually. Sir, can we use gas sensor in man? There are a lot of gas sensors are there available in the market, but basically we are working on fundamentally how to reduce the temperatures. Means like higher temperature to normal temperatures. Sarath Babu garu.
Any more doubts, sir?
I have a doubt. How many people understood? so, so thank you very much for the opportunity. Thank you.
Thank you, sir. That was a very informative lecture. You gave so many takeaway points. There are many takeaway points in the lecture, sir, like application of nanoparticles, comparison of nano with micro and milli, like why nano is superior in property, and how nature connects to nano, day-to-day life, how nanoparticles exist. Thank you, sir. Thank you for your lecture.
Thank you. I'm leaving.
Thank you. Good morning, sir.
Good morning.
I request Mr. Chandrakant to invite Dr. Pravinder Reddy, sir.
Thank you, madam. Good morning to one and all. It's a great pleasure for me to introduce our speaker, Dr. Pravinder Reddy, sir, who is going to deliver a keynote on measurability and experimental methods. Dr. Pravinder Reddy, sir, has received his BTech from KITS Warangal, ME from PSG College, Coimbatore, and PhD from Usmania University. Pravinder Reddy, sir, has 32 years of teaching and research experience, and he is currently serving as Professor, Mechanical Engineering Department, CBIT. Sir has served in various positions as Principal, Head of the Mechanical Engineering Department, and Dean R&D. Sir has over 315 publications, international journals, and conferences proceedings, and has published 6 patents. 32 scholars have completed their PhD under his guidance, and 21 scholars are currently pursuing their PhD work under him. Dr. Pravinder Reddy, sir, has delivered 125 keynotes and invited talks. He has a chief and principal investigator for 26 research and 131 industrial consultancy projects sponsored by AICTC, UGC, DRDL, BHEL, etc. Pravinder Reddy, sir, has received 17 awards that includes Raja Ram Bapu National Award and Engineer of the Year Award for outstanding contribution in education and research. He is a member of several bodies like DRC BOS of Usmania University and JNTU Hyderabad. He is also a research member of DRDL Council. He is a life member of several professional societies. So I welcome Pravinder Reddy, sir, to deliver the keynote speech. Sir, we welcome you, sir.
Yeah, thank you. Good morning. So they introduced me twice, yesterday and today. Good morning, all of you. Today, this session, I'll be speaking about some of the research which we have carried out on the metal matrix composites. You know, the machining of composites are very difficult, and estimation of the parameters for various applications. So machining is essential. The topic which I have selected for this session, machinability of metal matrix composites using numerical and experimental techniques. So all of you, those who are really working on machining of any alloys or composites, you know how the cutting parameters influence the machinability. And the same, suppose you wanted to simulate it. So in the simulations, we use implicit simulations and explicit simulations. I just wanted to present you, when you use the simulations, maybe a finite element analysis, implicit finite elements and explicit finite elements. When we model the cutting of any kind of process, whether it's orthogonal or oblique cutting, when we want to estimate the influence of the cutting speed, feed, depth of cut, you need to calculate energy. So in the finite element simulations, we need to apply thermomechanical analysis. When I say thermomechanical, we can apply for steady state conditions, transient conditions. So these are all the processes which I wanted to present you all. When we do the machining, experimentally, how the cutting parameters influence on machinability. Whenever we adopt numerical techniques, one of the important things in the numerical techniques when you adopt, we need to see the material models. Whatever conventional the modeling is not suitable for manufacturing process. So in the manufacturing process, always we have to see the non-linearity of the materials that we are machining. So I just wanted to give you the flow process using implicit as well explicit finite element simulations in addition to the experimental work. As you all know that composite materials are classified into two types: metal-based composites like solid metals with materials such as silicon carbide, aluminum oxide, etc. Non-metal based composites, we know the polymer composites, ceramic matrix composites. Metal matrix composites form one group of new engineering materials that have received considerable research since the first trial by the Toyota in the early 1980s. MMCs are multi-phase materials consisting of ceramic reinforcing fibers, or you can reinforce viscous, or particles or particulates suspended in a metallic or intermetallic matrix. Metal matrix composites offer various advantages in applications where high specific strength, stiffness, and wear resistance are required. In a present case, the aluminum alloy reinforced with ceramic particles is the most popular type of MMC used in aeronautic and aerospace industries because of its lightweight and specific strength. Its importance not only because of higher strength, the stiffness, and fatigue resistance with a minimal increase in density over the base alloy, but also due to low cost. Most of the aluminum MMCs, through manufactured by different manufacturing processes, usually need machining operations for the required dimensional and geometric processing as well as for good surface finish. So all these characteristics we are going to discuss in the following presentations. The machining of composites differs from metal machining significantly in some respects. Unlike a monolithic material, composites have fibers or particles present in the matrix that are encountered by the tool intermittently. That means when the tool passing through, when you use the cutting process. So fiber matrix interface, then matrix. So this combination, because the tool is subjected to some kind of the dynamics. The mechanism of chip formation also differs with fiber angle in reference to cutting direction. Here also we will see some of the observations. Once the rake angle is changed, how the chip flows, how the chip is separated. During the separation, that intermittent, what is the temperature, what is the stress level, what is the deformation level. So all these characteristics we can see in simulations. Anyway, any experimental work you can see even naked eye those flow process. And if you want to measure the flow stresses and all, again we need to go for the simulations. Low thermal conductivity of a composite material causes heat buildup in the cutting zones, which may also lead to thermal degradation of the matrix. Due to enormous difference in the coefficient of thermal expansion between the particulates and the matrix, the residual stresses are generated. So here one observation you can make, because it's a composite, we have a particulates with a different thermal conductivity, and the fiber, the matrix, what you can use is a different thermal conductivity. So here residual stresses are differed in a location to location. So local finite element model, whenever you go for simulations, is essential because we have to assign the properties accordingly. The amount of heat generated is different from normal conventional material when you use for numerical or experimental operation. In addition to above problems, the chips formed on cutting of composites are very small and are literally in the form of a powder. This hazardous airborne dust may cause inconvenience while machining and can be removed by a dust extraction system. Hence, the study of machining of composites as a whole needs to be addressed separately with that of conventional materials. With this background, we are going ahead for our research work. This work focuses on metal matrix composites with a higher percentage of silicon carbide particulates. The explicit simulations are carried out using LS-DYNA on aluminum silicon particulates. The scope of the study In this work, experimental and numerical studies are performed on turning of aluminum silicon carbide composite. In turning using K20 carbide cutting tool, the experiments were conducted to measure the temperature along the cutting tool edge using thermocouples at various cutting speeds, depth of cuts, keeping the feed rate constant. So we have changed even out of three, one constant, other varied. Then finite element simulations were carried out. Wear patterns and the wear land growth rates are also analyzed using both experimental as well as numerical simulations and evaluate the wear characteristics and to classify the relationship between the properties. And we have evaluated the flank wear land growth on cutting tools. The flank wear rate was quantified by considering the tool geometry. Further, the modeling techniques on continuous chip formation by using the commercial FEM code ANSYS LS Dyna are also presented in the following slides. A combination of three chip formation analysis steps, including initial chip formation, chip growth, and steady state chip formation, is used to simulate the continuous chip formation process. When I mentioned this, when your chips are flowing, when they are contacting the work and then separating from the tool, it's going to be some kind of the fracture mechanics we have to include. Here, this fracture mechanics is again damage fracture mechanics with thermal degradation. So this is a coupling of a lot of our engineering disciplines. In this cutting process, steady state analysis as well transient also performed to predict the variables contact pressure, we evaluate the normal stress, a tool chip interface and tool work interface using relative sliding velocity and cutting temperature distribution. So when we use the chip flow or the tool movement while keeping the work constant, there are two ways we can use in the simulations. One is you can have a dynamic mesh. That means when the tool is moving towards the work and there is a chip is flowing, to simulate such, the mesh is not going to be stationary. The element earlier in contact will go away further and the next element should come in. So here the moving mesh concept is being adopted. It is shown that tool wear rate is dependent on these cutting process parameters and the relationship is described by wear rate models. Then the tool wear progress in turning operation is determined. The aluminum silicon carbide particulates MMC material with aluminum 6061 as a matrix with 10%, 20%, and 30% is the silicon carbide particulates of size 10 to 30 microns dispersed uniformly. So the influence of this silicon carbide particulate 10, 20, 30%. When this size, how it is influencing on the temperature distribution, thermal stresses, and thermal distortion. Dry cutting tests at different cutting speeds, feed rate, and depth of cuts were conducted in order to investigate the effect of various parameters on surface quality. So we have measured the surface finish with those parameters while varying. In addition, the surface roughness of the specimens is evaluated with respect to volume fraction of silicon carbide particulates. The cutting tests were conducted using K10, K20, P20, P30 carbide tools and polycrystalline diamond tools to evaluate their relative performance. So comparison of all these, either you can measure the tool wear and the temperature and the thermal stresses and distortion, and we can conclude which is going to be the best material for the cutting operation of this and what conditions the tool wear is less and what rake angle it is. Again, the continuous chips are formed or brittle chips are formed and how the chip separation process is taking place. This is an experimental setup in our lab, and we have a HMT, the machine, and we have the stabilizer and the bridge circuit which we designed for the temperature measurement of using thermocouples on the tools. and interfaces also you can measure. So this is the schematic outline and the bit circuit what we have designed for measurement of the temperatures. And we need to calibrate, so we have an oven and keep the same and change the temperature and measure the voltmeter. Then you will be knowing the scaling and you can convert based on the temperature which we obtain, and you can connect to this, then get the true temperatures that we can get on the tool. So because as when we do the experiments, one observation that you can make it, because if there is going to be rubbing, there is going to be the interaction between the chip tool work. When you measure the thermocouples, because these are contact type, so we can have 3 or 4 thermocouples located in different places. So 1 or 2 when break, the other will have the temperature, so that we can take the average temperatures wherever we are measuring, because this is not a non-contact type, so it's a contact type. Okay, when we use finite element, I wanted to give some introduction about the analysis that we perform. We do the linear elastic analysis where the material is elastic and geometry also is linear. So we can have the general steady state when we do the cutting operations. The linear elastic analysis is enough to get the thermal stresses because we are coupling the after temperature analysis, the change in temperature delta T will be knowing, then thermal expansion we know. So this will be automatically is initial strain. With the initial strains, when you do thermoelastic analysis, then we can get the thermal and residual stresses. And the other is the nonlinear material, nonlinear geometry also. So nonlinear material, because we are saying chip is flowing. If it is a brittle, linear is enough. When the chips are in contact, then there's going to be deformation while machining. Then we need to have the nonlinear material models. So here, generally, the D is the material matrix. So this D, no more constant. It depends on either deformation or the temperature. The stress by differentiating strain energy density, you can use the linear material, you can use the nonlinear material. Then stress is a function of strain, the deformation dependent in case of nonlinear geometry. And you can model potential and path independent analysis. Typically, when you see the relationship stress versus strain, there is going to be a material matrix. This could be linear, this could be nonlinear. So if it is a nonlinear, there is a functional which we are going to use, then the material model and geometric model is going to be a nonlinear. In general, if you want a stress in terms of energy, du by d epsilon, and energy, you can write off of E epsilon square, when you have a relation between stress and strain with Young's modulus. The linear nonlinearity, to understand better, if you take a spring model, the spring which elastic E subjected to a load, when it is increase the load, there is going to be straining. And if you plot this stress strain curve, if this behavior is straight, it's going to be, we call it's a linear, but the behavior is a curve, then you would see here there are the different slopes, whereas the linear constant slope. So we have models in metal cutting, viscoelastic materials, could be time dependent behavior. Sometimes we have to model creep and relaxation models also. The metal nonlinearity in case of elastoplastic material. So when you take such a system loading, when you load it, then I unload it. So we have this elastoplastic kind of things where you are after yield point, there is going to be unloading, and either at yield or after certain point, we can do it. So this history is required for material behavior whenever we model for manufacturing techniques. The viscoelastic material time behavior or K relaxation. If you see here strain rate, you can have the time strain or a material modulus or a stress. we can measure with respect to time in this relaxation techniques and creep. We have some contact mechanics because here chip and tool and work, there is a contact. So what contact analysis generally we do, the same contact we can also mention, we can also include in our metal cutting process. So here when you use the contact, there is going to be, contact is always non-linear, and you have the displacement, load dependent displacements, and we sometimes model kinematic nonlinearity. So when you see this roller and subjected to a bar and it is undergoing, so you have a deformation, you can see the plastic deformation. And this is the contact mechanics and the plastic deformation. So you can plot the variation of the load versus displacement. You have typically have this kind of behavior. And you have a bar subjected to a continuous loading, and again kinematic nonlinearity. So we have some cases, mild nonlinear problems, may be continuous, still independent, nonlinear relations between the stress and strain. The nonlinear elasticity, geometric nonlinearity, and deformation dependent loads, all these are factors which we need to consider. And you have a mild to rough nonlinear problems, equality or inequality constraints in constitutive relationships. History dependent nonlinear relations between stress and strain should be included. Elastoplasticity and contact problems will come under this. And when you use a simple linear problem, K is the stiffness. Stiffness, as you know, depends on geometry and material. And D is the displacement, and there is a force. When you use in metal cutting operations, first we do the heat transfer analysis. So K is the characteristic matrix, T is the temperature, then thermal loads, heat flux, heat generation. So we measure the temperature change. After measuring the temperature change, then you can use the material property, thermal expansion or contraction. Then we couple these temperatures to the structural. When it comes to structural, we can do the linear analysis, nonlinear analysis. If you use the linear analysis, the stiffness into the displacement is equal to thermal loads in addition to the cutting forces. Cutting forces, static forces. Because of contact, temperature induced, there is a change in temperature. You have a thermal load also. So here, this resultant load is load due to temperature change and in addition to that cutting forces, both together. So we can get the deformation, then strain stresses. These are the thermal stresses. And you can use nonlinear analysis, where when you use nonlinear analysis, the load and the stress depends on displacement. So these kind of solutions required either use incremental method or the familiar approach like Newton-Raphson method, modified Newton-Raphson method. Those approaches we use. So in nonlinear cases, equilibrium between internal and external forces, kinetic and kinematic nonlinears are included, appears on the boundary, handled by displacements and forces, either use the global static or steady state implicit, or you can go for explicit. Relatively easy to understand, not easy to implement though. Material, geometric nonlinearities appears in the domain, depends on stresses and strains. These are local and implicit analysis. Typically, if you see the geometric nonlinearity, typically a rod, when it's subjected to a moment, it takes this kind of large deformations, large strains. So those are all called the geometric nonlinearity. So if you can see the tip displacement versus the applied load, you have typically a curve. If you see the incrementally, then you can have a load increment, but basically load is constant. So what in the simulations or in the periodic of experiments when you conduct, we typically, the actual load, instead of applying the actual load, you increment it, then go to the final load. So then you get actual displacements. So mathematically you can say linear, simply epsilon x, then one dimensional typically. du by dx. But if you think non-linear, the error terms are removed here. So you can include the error terms. So these error terms will make there is a deformation large. The displacement strain relationship, you can see when you apply strain versus du by dx, how much deviation that you can see. And this E, when you wanted to calculate, then the Young's modulus, what actually you can predict or you can estimate. So you know epsilon x is du by dx, that is going to be strain actually reaching when the actual slope is going to be constant. When you calculate the energy or the stiffness for the member, then you can take volume integral or surface integral depending on our line integral. Depending on geometry that you are considering, then the other domain, then strain and stress, and for the same domain. So you have a strain transpose and sigma. Here non-linear because this stress and strain are depends on geometry or displacement. When you analyze, that's a structural part of it. Then you have a thermal part because our material getting constitute both thermostructural. So we need to do the heat transfer analysis. Sometimes we satisfy steady state heat transfer, but in reality we have to go for transient heat transfer. Now both the cases, you can have a linear analysis, non-linear analysis. What is linear steady state heat transfer analysis? Your material properties independent of the temperature. What is the material property required steady state condition? Only thermal conductivity. So thermal conductivity is the independent of temperature. And you have non-linear, means you are thermal varying with respect to temperature. So non-linear material. So then we have a transient heat transfer. In the case of transient heat transfer, linear. So here the material is linear. So in the case of transient, the material properties required are thermal conductivity, density, specific heat, or enthalpy, because there is a phase change. So that's why enthalpy or specific heat are required. So in linear analysis, your thermal conductivity and enthalpy or a specific heat and density are independent of the temperature. Whereas in nonlinear, those varies with respect to temperature. So when you want to have cryogenic conditions, you are cutting operations, we'll do a different temperatures. There the material might lose its property, and accordingly we need to have the real simulations. Typically, if you use the steady state heat transfer analysis. Hello? Anything? Okay. So when you use the steady state heat transfer analysis, typically if I take some volume and temperature anywhere, let us say T, X, Y, Z is your geometry, and small q is the heat flux, capital Q is the heat generation, and H is the convection. So in our thermal cutting, when you do the operation, H is going to be, when you use the fluid, right? So we use the fluid, so you need to use H. And contact, you can calculate heat generation or heat flux. Suppose if these are the conditions acting in our cutting process, we have the energy equation, the 3D conduction equation. So Kx, Ky, Kz thermal conductivities, T is the temperature, X, Y, Z your geometry. So we can write the energy equation as Kx dou square T by dou X square plus Ky dou square T by dou Y square plus Kz dou square T by dou Z square plus or minus Q equal to 0, heat input. This is going to be your geometry. If it is a 3-dimensional, all the 3 terms. If it is a 2-dimensional, first 2 terms, 1-dimensional first term alone. If there is a coolant, then we have to use the convection. In the same equation, we are using convection. The T infinity is the bulk temperature. The fluid coolant temperature, you can say fluid temperature or coolant temperature. So here heat generation, heat flux, heat generation is per volume. Heat flux is per area. And convection is per area. Then you have a T temperature wherever you wanted to calculate. T infinity is the coolant temperature. So because steady state right hand side is 0, if it is unsteady state right hand side, you have a load dependent term will be there. And we need to solve this for the temperatures. So whenever you want to solve any the governing differential equation, we are going to use either two approaches, energy or weight approach. For doing such, we need to have a boundary conditions. The boundary conditions in any heat transfer analysis are specified temperature, maybe room temperature, etc. Heat loads, how much is the thermal load, heat flux, heat generation, insulation, somewhere it's the furthest, no contact, or there's a contact, then you can say heat flow is zero. Then sometimes we need to include radiation also. So here, this governing differential equation, the first part is heat due to conduction, geometry. And the second is heat due to generation, load. Heat due to heat flux. This is again load. And this is a convection load, heat due to convection. So we can use the variation principle or work principle. Then you can calculate total energy in the system. The energy in the system is the volume integral of your kx dou t by dou x whole square plus k by dou t by dou y whole square plus kj dou t by dou z whole square over volume minus volume integral q into temperature dV minus area, because q is area dependent, qt dA, and again h is surface dependent of area integral ht minus t square dA. So this is energy due to conduction, energy due to heat generation, energy due to heat flux, energy due to convection. All the summation of all these is going to be total energy. When you use a finite element analysis, you discretize the given body into small, small pieces. So what you have to do, this energy you have to calculate for the first element, then second element, then third element, and fourth element. And then total energy we need. So here, suppose you wanted to come to a certain concluding part of the terms related, instead of using all these variables. So here, the first one, the energy due to conduction, we say pi 1. The second is pi 2, third is pi 3, fourth is pi 4. The phi 1 alone, you wanted to simplify, which is the same thing written here. Then this we can write in a matrix form. So I'm writing here now the row matrix dou t by dou x, dou t by dou y, dou t by dou z, and the material matrix kx0, 0, k0, ky0, 0, 0, kz. Then again the column matrix of the temperature gradient. Now we designate this as the temperature gradient G. G is dou t by dou x, dou t by dou y, dou t by dou z. Temperature gradient x direction, temperature gradient along y direction, temperature gradient along z direction. And here this is going to be your thermal conductivity. If it is orthotropic, you have a thermal conductivity x direction, y direction, z direction different. Isotropic, it is going to be only one thermal conductivity. So D becomes K. And this we designate by capital D. Again, if this is going to be G and this is G transpose. Right? So now this same, if you multiply this into this and this into this, you will get the same. So whatever equation we have written in matrix form. Then this we can simplify half of volume integral G transpose dG. That's what we have written, the gradient matrix dou t by dou x, dou t by dou y, dou t by dou z. Typically, if you take one element, maybe tetrahedron element, 4-noded tetrahedron element, the geometrically x, y, z, three-dimensional, and you have coordinates x1, y1, z1, x2, y2, z2, x3, y3, z3, x4, y4, z4. The temperatures T1, T2, T3, T4. As you know, we use the shape function. The shape function is, because you have 4 nodes, 4 shape functions, n1 to n4. Then T is the element temperature anywhere. So nodal temperature T1, T2, T3, T4. So as you know, that element temperature is equal to nodal temperature into the shape functions of nodes. So here temperature anywhere in the element is the shape functions of the element into nodal temperature. So nodal temperature, you can have the expansion N1 T1, N2 T2, N3 T3, N4 T4. It is separate. the shape function separated with the column matrix of temperature. NT bar, you can write. The gradient matrix, now dou t by dou x, dou t by dou y, dou t by dou z, dou t by dou x, we can write dou n1 dou x to dou n1 dou y. Dou t by dou y, dou n1 by dou y to dou n4 by dou y, t1 to t4. Similarly, dou t by dou z, this row into column. And here the gradient matrix is split into the B matrix, this is the temperature gradient matrix, into nodal temperature. So this matrix I've written here, this is going to be strain displacement like here temperature gradient matrix. Then material matrix, if it is isotropic, D becomes only thermal conductivity. Then we can write the simplification of this, the phi 1 is half of volume integral G transport dg dV. So the total energy, now we can substitute here, then loads, we can write the load, we can write, and the temperature is NT bar, right? You can write in terms of shape function and nodal temperature. Then you can write T transpose T bar temperature, the T bar into N here, T transpose is T bar transpose N transpose, N is missing here. G is BT bar, G transpose T bar transpose B transpose. Substitute in the above equation. And this results, this we can simplify. There's the total energy summation of those. Once you get the total energy, then differentiate the total energy with respect to nodal temperature, then equal to 0. That is your energy principle. So once you differentiate, then equal to 0, it results in this form. The first part is volume integral B transpose dB dV. The second part is area integral H N transpose N dA into temperature in the structure equal to then the load due to heat generation, load due to heat flux, load due to convection. When I convert this to metal cutting operation, this part is your geometry, tool, chip and work. This part is your coolant. Suppose no coolant, this is 0. And no coolant, this is 0 and this is 0. And here the heat contact, this is contact between the tool chip and work. These are the contact heat loads. And these two are coolant dependent. No coolant, these are 0. So that's what convection values. So this is the convection, the convection part of conduction. And this C1 plus C2, you can say C into T bar equal to load. So we can say it's going to be load. And these loads are, the first load is due to heat generation, second load is heat flux, third load is convection. That's what I mentioned here. Then you can combine these two, the characteristic matrix into nodal temperature equal to load matrix. So simply CT bar equal to F, solve for T bar, then you can get the G, then you can get all other gradient, because temperature gradient is required for us. This is going to cause thermal stresses, thermal strains. So we need to get this G value after getting nodal temperature. Then you can calculate the heat flow rate in our heat transfer analysis. Then we can see that once we couple to structural, then switch from thermal to structural, then we can get initial strains due to alpha and temperature change. So here the temperature change is this G. Alpha is a material property. So sigma equal to D into epsilon minus epsilon. Epsilon is the normal strain and epsilon naught is initial strain. This is your material property. So that causes thermal stress. So this is what we use in steady state solutions. But is it steady state enough for our metal cutting operations? Not. So we need to go for a transient. And we wanted to measure tool wear rate. Again, it is time dependent. We need to work transient analysis. The field problems considered earlier assumed to have reached the steady state condition before the analysis is undertaken. An equally important set of physical problems include those that are time dependent. The transient period for some of those problems occurs between the starting of the physical process and reaching the steady state condition. A steady state condition never reached in some problems, and the transient period includes the entire life of the process. The tandem problems are common and important in heat transfer. The quasi-harmonic equation contains time derivative term in a physical system. So this total, whatever you use steady state, the right hand side we have this the gamma, the and dou T by dou of T. So here dou T by dou of T is the time dependent temperature load. So this becomes the transient. And this is heat capacitance. Lambda is nothing but rho C, density into specific heat. So in our materials, the uh, density of the material and the specific heat of the material. So when you take work density and specific heat. When you go for the tool density and specific heat is going to be long. And your thermal conductivity is then heat energy. What is the difference in case of transient? Whatever right hand side is there, you take on the left side. The heat generation already is there. Because right hand side you are converting to left side. So this Q minus lambda dou T by dou T is the new term. This we can integrate and again use the same minimization process, and we can calculate heat loads from that, and we can couple. So whenever we use, these are all same as earlier. This K is C and phi is the, because why we modified phi, this is a transient one, and this is going to be load. This is a characteristic matrix. This is a temperature, time dependent temperature. So here the characteristic matrix into dou phi by dou T, time dependent temperature, we need to estimate. So for calculation of those, we have an additional term of capacitance matrix. So this capacitance matrix is volume integral. If it is 3-dimensional volume integral, 2-dimensional area integral, lambda into shape function transpose into shape function over volume. So lambda is rho C, and here this is the additional one in transient case, and that need to be included. Whenever you include time dependent one, we need to solve this either incremental step process, or you can go for any different scheme. So we use for the elements, the final equation we can write like this: C phi dot means the temperature dependent, time dependent temperature, and this is steady state. And this is the transient term of capacitance matrix. Capacitance, temperature, time dependent temperature is the additional term. Rest of the things same. So we can use forward, backward, central difference schemes to estimate by giving increments of the time, and you can calculate, because here additional boundary condition required is initial boundary conditions. Initial boundary condition nothing but at time t equals 0. What is the status? Solve first for that first iteration, then increment it. So we use both backwards, central difference, and or otherwise we can use forward difference method, Ehler's method, Crank-Nicholson scheme, Galerkin's method, backward difference method. So where we have given this equation in a generalized form, the theta values for those whenever we adapt, and that will be coupled. See, abacus or LS Diana, when you take all these models exist. Okay, with this background, we'll move on to the chip flowing process, real cutting process. This is conventionally when you see a small chips, this is the work, then the tool, then you have a chip. If you see here, the mesh density is going to vary, because here there is a shear zone. We need to have a more number of elements, and this side cutting, this is a contact between the tool and work. You should have more elements, and you have a contact between tool and chip, so you should have more elements. And for this we have removed, for this we have removed, and we are trying to have more number of elements, because this is a zone our important, and this zone is not at all bothered. Only for the sake we need to have some shape we have kept, but otherwise our total interest is only this part. So localized mesh, we need to have a grid size, the very refined mesh. And when you use the models already in LS Diana, there are 64 material models you have. Even Abacus also similar. We can adapt some of the material models so that the coefficients will be available. These material properties we can assign, and the indices we need to specify. Typically, JC ordering method describes flow stress of material with the strain rate, temperature effect. So this is going to be the constants A, B, and you have a C, and the ABC are given in the material strength values. So if you see sigma bar is equivalent stress, A is the initial yield strength for that material we know at room temperature. B is the hardening modulus. Epsilon is the equivalent plastic strain which we are going to measure. N is the work hardening component exponent. C is the coefficient dependent on the strain rate, and epsilon dot is the equivalent plastic strain rate. And again, we can have a reference strain rate. M is the thermal softening coefficient. And the room temperature and all we specify for the same. And the coefficients here again, when you go for the strain rate for fracture, when you have a damage mechanics is associated. We have the parameters like D1, D2, D3, D4, which we can have the constraints for these models available. And we can include these when you select that model, automatically these constants will be given. And we can calculate the deformation in terms of strain rate and fracture, the damage, because the chip, when it is separation, we are going to calculate the damage mechanics. So we use Hilbert's fracture energy. This is strain energy release rate. We will calculate for the slope of the same and the yield strength and the strain rate in plastic zone. So when we calculate the damage, the contact mechanics into the chip and tool contact, so automatically these we can select in our abacus model. Then the failures can be estimated. And the pattern of variation, so the progressive damage, especially for this is going to be a chip model. So what we are doing for the chip and work and chip and tool, only that portion we are going to have a localized fracture model. So fracture contact and all in, when you connect thermomechanical, the mechanical analysis, structural analysis, we need to include these terms. So elastic models, how it is increasing. We know the theoretical equation, the strain energy release rate with the stress intensity factors for plane strain and plane stress, the small variation we are going. So this is for the damage, and the other side, we need to define in our heat transfer analysis the heat flux. So we need to calculate heat flux between the tool and work, and heat flux between the tool and chip. So, and it is shear zone. So we have even any, this is one thing I have given here, any metal cutting book, you will find all these, the heat flux along the tool work interface, chip tool interface, shear zone. Even those, whatever, those are mentioned here. And because when you go for a transient condition, this is a steady state condition. But when you go for a transient condition, that heat flux, the rate, because we need to model the chip rate and all, the specific heat we have to define and you can model. So according to the temperature change, the difference, what we can calculate. When you again link with this thermal variation in transient condition to the damage mechanics. So thermal and fracture, we have to couple and we can calculate. Generalized boundary conditions, but coupling all the flux have written a generalized way. Q of plastic is you have the mechanical coefficient and stress at the plastic equivalent the strain rate at the plastic rate, and heat rate per unit area and chip tool interface. So here fractional heat per unit area, you have a fractional coefficient, then you have a shear at that location, then you have strain slip rate. The material properties you can take, we can have steady state condition, the independent of the temperature, all the properties we can take, both aluminum, silicon carbide, then the tool materials, all the tool materials we can have the properties to assign, or you can select. Then experimentally with the bridge what we have defined when we operate at a different depth of cut and feed rate and varying the cutting forces, we can measure the temperature. So the temperature at different cutting speeds, because at the interface, midpoint of the interface. So we have given from the contact furthest away and you can have an average of these temperatures, tool temperature, tooltip temperature. So otherwise, the nearest and further away, we have calculated different speeds. So when you increase the speed, definitely you know that the temperature is increasing, and you can see the temperature variation between when the speed is 9.8 meter per minute, it's 165 degrees centigrade, and 50 meter per minute, it is increasing to 285. When you showcase the same in fundamental modeling, so here the damage mechanics, earlier I've shown is steady-state heat transfer. When you want damage mechanics, we need to have a contact location for this and the very fine mesh. And when you have a tool, you can also see the tool. We have very high, because chip point tool is going to have a contact. That's why it meshes. And this tool is now moving so along the, if you say the radial direction, it is moving in the radial direction. And some of the analysis we performed with changing the rake angle. So when you change the rake angle again, remesh it, again you should have a contact, then you have to have the models. And we can measure the wear also, flank wear, right, and nose wear and all. So when such a model with different strain rates, we can calculate the full flow stress values at different temperatures. So when you plot flow stress versus effective strain at different temperatures, we can see at different strains, higher strains and lower strains when you observe, right? So this 10 to 5000, here at the lower, the higher temperatures, almost these are not affecting anything. But lower temperatures, if you see, there is going to be the variation among the strain rates. So that's the observations you can make it. When the chip is flowing, and you wanted to see the strain energy release rate, so energy, what we can calculate at different locations. When your chip is curling and even, so there is going to be a separation, break, connecting at certain points. And here you have a continuous form. So if you see the lower energy, it's a breaking and discontinuous. And at the higher energy level, you have a continuity, so plastic deformation, and it is going to be very continuous. But high values at this place, high energy values. So you can see again for the rest increase in and 20,000 and 20,000. And you can also see the stresses induced. So almost it is highest at this level is around 70 megapascal. Similarly, this is going to be at different depth of cuts. So here, this depth of cut is 20 microns. Here, depth of cut at 20 microns and 50 microns. The energy is 12,500 per meter. And you can see at high depth of cuts, you have a chip separation, whereas their continuity is being observed. And here, again, with the constant energy and constant depth of cut, changing rake angles, zero rake angle, you have this pattern. 22 degrees, you have continuous, and again, there is a breaking, so somewhere. And you are at minus 30 degrees. You can see, again, it is coming back, and there's no continuity. And the minus value, so minus is not real simulation, what the real, how the actual work is in a progress in experimental. And again, here you can see chip fracture during serrated chip formation at different strains. So you can find out chip fracture taking place. There's going to be a connecting here. Okay, and you can see here because here you are getting rake angle 20 degrees is fine. Keeping 22 degrees, energy is 1500 is fine. So 1500, depth of cut 20 microns is fine. So, and we can calculate the plastic strain, how the plastic strain is going to be. So this is the real behavior, what is required. So this is the real behavior. We can fix it and we can proceed further. And when you compare the results, both experimental and the fundamental simulations, particularly temperature distribution. So we have plotted the temperature against the depth of cut. So this is experimental values. And we can see from the radial direction how the temperature is varying at different cutting speeds. And similarly, axial direction. And also we can measure the chip thickness, so chip flowing process. The temperature chip tool contact is very high, and as one moves further away from the contact, there is a gradual decrease in the temperature. From these figures, one can observe that most of the heat concentration in the tool, this phenomenon is entirely different metals, where most of the heat is carried out by the chip. The reason for this behavior could be due to the difference in cutting mechanisms. In the composite materials, the cutting mechanism is more of brittle fracture, involving a combination of mechanisms like cutting, cracking, flowing, and abrasion. These are the four mechanisms observed in the cutting process. Very small contact length between the chip, dust or minute size of the chip, and the tool can also be explained as one of the reasons for the heat not being carried by the chips. And cutting temperature versus cutting speed, when you compare both experimental as well as numerical. So we have almost closed relationship, almost 1.5% variation here and there. Some places coinciding, some places deviating. After measuring the temperature, so then the stress strain rate and all, we need to estimate the wear. So you know the chip compression process and merchant tool, where the tool, how it is going to mount. So the objective of this experimental work is to compare the results of the merchant equation with the experimental cutting model during the turning of metal matrix composites with the PCD cutting tool. So here we conducted experimentation on aluminum composite with 70% aluminum and 30% silicon carbide with a diameter of 60 mm. The tool tips are square inserts 12.7 by 12.7 mm and 4.7 mm. SNP of 432 type with a tool geometry of 5 degrees, 5 degrees, minus 5 degrees plus, and 15 degrees and 0.8 mm, which are set in standard tool holder. The material of the tool tip is K20 carbide tool with a composition of 94% WC and 6% cobalt. So a depth of cut of 1 mm and feed rate of 0.1 mm per revolution remain constant through all the tests. Several spindle speeds are selected. Cutting fluid is used for washing of the chips. The flank wear lengths of tested tools were measured with Olympus STM tool makers microscope. The nose wear by Protosys subcam 2B submeter, and the work cutting edges obtained by Hitachi Akashi's MSM2 scanning electron microscope. The theoretical equation, what you have, cumulative damage of tool is summation T equal to 1 to K, because we are going to connect the through contact the delta T1 dCt to the power 1 by n. In other words, Q C to the power 1 by n. So these are the material properties of the tools which we have used: carbide tipped K20, P20, M10, then ceramics, aluminum oxide with we have a titanium carbide. These properties are required, and you can plot nose wear and sectional area of the nose wear at different cutting speeds. So the cutting speed selected 14 RPM, 800 RPM, 2000 RPM, and you can observe that against number of cuts, when you increase the number of cuts, the nose wear is increasing. But increasing after a certain level, you can observe after this, it is again decreasing. Whereas the sectional area of nose wear is increasing. These dotted lines are sectional areas. So there is a constant slope, right? So this is linear. This is a small variation of these two, okay, at different speeds. But otherwise, you can say at a lower speed, right, and higher speed it's going to be very high. And nose wear land, you can observe at this location it is going to be very, very high, and that you can see the next slide that on the tool, the land wear on the edges, you can have a lot of cracks. And you can observe even more. This is a nose wear. And banded wear and carbide tool. So it is bonding like, so attachment. Okay, so there's no cracks and all. The compare wear rate on HS and K20 tool materials. These two are, you can have a comparison where you can find the deposition of. When you discuss these results, the wear progression, different volume fraction of silicon carbide. So volume fraction on the x-axis, you have a 10% and 20%. So then we have a measured one and a predicted one. So flank wear in mm, so you can observe the measured one. When volume fraction is increasing, it is increasing. In both measured and predicted. If you see here, we have progression at 10% dispersion of aluminum. So the measured is a black and white is predicted. You can observe here at volume fraction 9.5, 20, 25. Again, it is increasing. The level of increase and all, also you can see the magnitudes. We are the same flat wear rate, you can also see. Measuring at a different micron level. So we have 20, 25, again 20, 25, both measured and predicted. The progression of the tool wear is highly dependent on the volume fraction and average size of the reinforcements. Volume fraction and average particle size increases, the rate of flank wear is also observed to be increased. The increase in the volume fraction increase the number of hard particles coming to contact with the cutting tool. This results in a higher volume of tool mechanism, sorry, higher volume of material. This results in a higher volume of tool material being lost due to the abrasion of mechanism. From the, it is noted that the fine and well-distributed particles in the matrix reduce the tool wear and improves the machinability. It has been found that the coarser the particle, the more severe is the tool wear, and hence the better is the tool life. The cutting tool, when you cutting forces, when you measure against cutting speed, so it's a different kind of observation you can make it. So the main cutting force, feed force, thrust force, these forces are in the order it's given here. By cutting speed, generally contact is increased, rubbing is there, cutting force supposed to increase, but surprisingly here, the cutting forces are reduced. These experiments conducted depth of cut 1 mm, feed 0.1 revolution per minute, the volume fraction at 70%. If you see the wear of primary and secondary, against the cutting speeds in meter per minute. So you can see the primary wear is high as compared to secondary wear. And again, you can also observe both of them are increasing at 250 meter per minute, and afterwards it is decreasing. So from those graphs, we can observe that the primary wear is maximum at the speed of 250 meter per minute, and the minimum at the cutting speed of 300 meter per minute. The secondary wear also maximum at 250 meter per minute, and it is least at the speed of 300 meter per minute. The cutting speed 250 meter per minute is critical speed at which the grow wear and nose wear rate is maximum. This is attributed to the failure of cutting edge as a result of softening of tool material with an increase of cutting temperature, and it is concluded that the critical speed is proportional to the hardness at room temperature. The hardness is proportional to the compressive strength, as you know. Hence, it is supposed that the compressive strength must play a significant role in increase of the critical speed, which shows the high speed cutting ability while machining of metal matrix composites and cutting of relatively high thermal conductivity materials. The heat transfer from the cutting zone to the tool is resisted with the use of tool material with low thermal conductivity. The same for tool wear, we wanted to model, simulate and find out the wear rate. So the fundamental modeling which we have done for the same and using ANSYS LS Diana, we performed the analysis. The work is measured with the plane 162 element. Work consists of 4025 elements and tool 615 elements. The contact elements are used at the tool chip and work tool interface. Fine mesh is used at the tool tip. And formulation, Lagrangian, Eulerian, arbitrary Lagrange Eulerian, all the three are possible. Many researchers have attempted Lagrangian formulation, but it requires chip separation criteria based on shear failure, in which corresponding elements are deleted when shear stress crosses defined failure stress criteria. Accuracy depends on the size of the elements that are getting deleted. Even though fine elements give better accuracy, the computation time and cost is also accounted. Mesh distortion is another problem in Lagrangian formulation. When it comes to Eulerian formulation, it doesn't require any chip separation criteria, but the geometry of the chip should be known prior to the analysis. Hence, in this one, the chip geometry is obtained with the ALE formulation, and further analysis of wear is carried out by Eulerian formulation. You can have the models for the initial chip formation. So this is going to be ALE model. Tool is taken as the resid and moved. Output file with the geometry. Nodal results are written after chip formation. So then we have a contact between them. So when you delete and others, they have to grow. And if you see the second one, the chip growth, the output file of previous simulation is imported. The tool is fixed, and the left and right boundaries workpiece are defined as Eulerian models. The work is fixed in y direction along the bottom surface, and the material moves from left to right. The simulations continue till the steady state is reached and the output file is written. Then again, we go for the steady state chip formation. The output file of previous simulation is imported. Tool is taken as a deformed material. Top of chip is constrained and the Eulerian boundary condition is applied. The tool is fixed along X direction on the right hand side face and Y direction on top face. These are the models corresponding to it. And typically the governing equations used in our the constitutive relationships are those, and accordingly the Johnson-Cook model is taken. The constants A, B, C, N and M, the remaining are estimated from the analysis. And this is a wear rate which we can calculate with C and gamma are constants, and W dot is wear rate, Vs is the relative sliding velocity of the tool, and sigma F is the normal stress, theta F is absolute temperature. The sigma F, theta F, and Vs are obtained from the steady state chip formation analysis. Wear is calculated by multiplying with the time at each time increment. Then you can calculate those. These are the rate phases where the nodes identified, and the normal to that, when you couple to the previous, they are going to correspond to measurement of the direction, the W, the direction which we can take from those nodes. The wear direction of each node is taken as the opposite to the resultant of the normal of connecting segments. Corresponding to the tool geometry is updated, moving the face nodes in wear direction, and the simulation is continued. And we can plot the flank wear width measured and estimated, and here also crater wear depth against the time. So we can calculate the rate of that and we can showcase. After that, we have measured the surface finish, the quality of the components produced during the turning. Aluminum silicon carbide particulates, MMC, is important as it influences the performance of the finished part to greater extent. Estimation of surface integrity can cater to the requirements of performance evaluation. Surface roughness is the final surface quality formed after machining. The surface quality of a specimen directly related to cutting speed, feed rate, and depth of cut. The aluminum silicon carbide particulate MMC material with aluminum 6061 as matrix with 10, 20, 30% silicon carbide particulate of size 10 to 30 micron dispersed uniformly. Right running tests at different cutting speeds, feed rate, depth of cuts were conducted in order to investigate the effect of various parameters on surface quality. Surface roughness of the specimens is evaluated with respect to volume fraction of silicon carbide particulates. The cutting tests were conducted using K10, K20, P10, P20, P30 carbide tools and the polycrystalline diamond tools to evaluate their performance. The surface roughness, this is going to be the late mission. The P-type tools and K-type tools showcased, and the results obtained are the work materials were machined at 4 different cutting speeds, ranging from 20 to 110 meter per minute, with feed rates ranging from 0.05 mm per revolution to 0.4 mm per revolution. Each experimental trial was carried for 3 minutes duration. The average surface finish in the direction of the tool movement was measured in 3 different places of machining surface using a surface roughness tester. Finally, mean surface roughness in microns of the 3 locations were considered for each case. This is going to be surface roughness measured using surfatronic turning of 10, 20, 30%, as I mentioned. The surface roughness 20 meter per minute and at 100 meter per minute at different cutting speeds, and changing field rate you have, and the same at a different percentage of silicon carbide particulates. Surface roughness samples which have higher reinforcement ratio have higher which have lower reinforcement ratio. It may be due to fact that the tool is not cutting through silicon carbide particulate rather than peels off from the matrix. Higher the reinforcement, higher the number of pits formed, so higher will be the surface roughness value. We show that some of the silicon carbide particles are being pushed partially into the matrix while tool moves on the surface of the specimen instead of all being peeled out. It is also observed that the effect of peel on the surface is more predominant at higher reinforcement. And these are machining with K20 carbide tool. You can see here the work and the tool. The machining with P20 carbide tool, you can have the tool and work inserted. Again, tool you can see with K10. So 10%, 20%, 30% with the different cutting speeds and the feed rates, we can observe the surface roughness is decreasing while cutting speed is increased. And you can also observe that at 30%, it's going to be better. So we have calculated at the different feed rates and keeping feed rate constant, depth of constant, all the parameters have been studied. The depth of cut is increased to 1 mm, more will be surface roughness. It can be seen that the surface roughness ranging 0.8 microns to 0.5 microns using P30 grade carbide tool. At 0.15 mm per revolution using the same tool, the surface roughness ranging from 0.9 microns to 0.6 microns. K20 carbide grade tools, it is seen that the surface roughness ranging between 1.6 to 1.4 microns. So each tool we have conducted, even PCD you can have, when all the other parameters kept constant, including the feed while machining with the PCD as a tool with feed rate of 0.05 mm per revolution, depth of cut 0.5 mm, the surface roughness of the components was observed to be comparable to use those obtained from P30 grade carbide tool. The relative performance of the different tool materials with regard to the associated surface roughness may be attributed to differences in friction behavior between the tool and the workpiece materials. So 30% with 0.5 mm, and then here 0.05 mm feed rate, and feed rate is increased, and here cutting speed is increased. Okay, so depth of cut is increased. So to conclude, the maximum temperature is observed at the chip tool interface at a cutting speed of 50 meters per minute. That is 315 degrees centigrade. The temperature is gradually reducing along radial and tangential to the direction to the tool contact to the work. The temperature is also reduced from the chip tool interface to the tool flank and radial to the work. The experimental results are correlated with finite element results, and variation observed to be at steady state condition at 1.2%. It is observed that the most of the heat concentration is in the tool This phenomenon is entirely different in metals, where most of the heat is carried by the chip. The cutting temperature increase with cutting speed increase is less significant in feed and depth of cut. As the FA model is being validated, it can be used for the estimating temperature in metal cutting while machining MMCs with a different percentage of silicon carbide and aluminum particle weights. When cutting speed is increased, the nose wear will be the shape of the triangle and its wear rate increases. Higher the thermal conductivity and the compressive strength or smaller the thermal expansion coefficient, higher the critical speed. The thermal conductivity is the most important among them as a factor to rise the critical speed. In cutting conditions of the critical speed, the groove wear on end of the cutting edge grows larger with the decrease of cutting speed. The groove wears in the shape of round or bands. The wear rate is measured at the cutting speed of 250 meters per minute and minimum at 300 meters per minute. Finally, the tool geometry is updated according to the calculated nodal displacement and one calculus cycle is finished. The program continues until tool reshape criteria are met. The user program continues until tool reshape criteria is reached. The number of calculation cycles carried out before user program stop is defined by dividing tool reshape criteria by the specified BN increment. The surface roughness decreases with increase of cutting speed, but increases with the feed and depth of cut. Among the feed and depth of cut, it is found that the feed is more severe than the depth of cut. The surface roughness value depends on volume fraction of silicon carbide particulates present in the matrix. It is found that surface roughness increases with increase of percentage of silicon carbide. Surface finish obtained with the P-type grade carbide tools better when compared with K-type carbide tools. It is recommended that for roughing cuts, K-type grade tools and for finishing P-type carbide tools can be adopted. Surface finish obtained with polycrystalline diamond tools is better when compared with carbide grade tools, but it is found that it has feed of 0.05 mm per revolution, a depth of cut of 0.5 mm. Same surface finish can be obtained with P30 tool as that of PCD tool. It can be seen that P30 carbide grade tools can be used at certain cutting conditions, which can replace costly PCD tools and hence reducing overall cost. Thank you. So any questions, queries, welcome you all.
Any questions from the participants? Please ask.
Yeah, good afternoon, sir. This is Madan Mohan here. Hello?
Yeah, please.
Sir, as you mentioned in the material non-linear, the viscoelastic material, you mentioned that a time-dependent material. All materials are, time-dependent.
No.
So how specially that you can explore that certain metals are only time-dependent, certain metals are not time-dependent?
Actually, the materials time-dependent and all, it only while which process that you are considering. Whether you want
No,
time
actually,
dependent or not.
sir, my point is viscoelastic material, once you said the time-dependent material, it means particular material only time-dependent and but not other time-dependent. All materials are time-dependent, I think so.
No, materials time dependence and all not the criteria here. When you consider creep, it's going to be strain rate. Then the materials, the flow rate and all we required. Then time dependence is required. Same viscoelastic material, if we use for only elastoplastic condition, time dependence is not required.
Yeah, temperature dependent material we have to consider, no?
No, temperature dependent material because that also depends again. Suppose your cutting conditions are at different levels where material changes its property. Then we need to consider temperature dependent material properties.
Okay. So I think not certain metals are time dependent. All materials are time dependent, right?
Yeah, the time dependency and all, suppose what process we are doing. Material, fine. Material, you can take all time dependency. In the all materials can have time dependency. That is only
And,
a process dependency.
I got it. I understand very well. Sir, I would like to ask you one more question that how can you choose that this particular P30 carbide and K20 carbide are the suitable material where we can reduce the cost for the cutting tool instead of PCD tool?
Correct. The cost point of view.
Yeah.
I didn't get your question.
No, my question is that how can you get the idea that P30 carbide and K20 carbide are the suitable material that we can use for this particular project? Exactly.
No. Actually, if exactly means literature, the people have used for different silicon carbide particulates. So they have used even these tools. So based on that, and we tested here with the different tools and compared the otherwise.
It was a lot of work, sir, to analyze these particular tools among different, right?
Because this is the series of number of PhDs have integrated. Okay, so it's not one work.
Yeah, it's a very huge. That's what I'm asking.
Integrated are present to all. So we worked on the carbon composites. We worked on different kind of composite materials. All right. Okay. So there different tools are used. So when we go for the next research, the same tools and add some more tools. Like that, we have progressed with the different tools, and the same I have presented here. But each case need not use those the tools. And also second, availability.
Okay.
And because one advantage, all these materials available from Midani and in Hyderabad, the DRDL. So it's possible that they are also working on it. And sometimes they suggest that let us use these tools and give us some data. That's also another point here for working.
Okay. Thank you, sir. That was a great work, sir. Thank you.
Okay.
Any more questions from the participants? Okay, if no more questions, I would like to thank Dr. Pravinder Reddy sir for enlightening us with his presentation. It gave us good scope of research in the area of metal matrix composites. Sir, it was really beneficial for the researchers working on machinability of composite materials. On behalf of all the participants and organizing committee, I would like to thank you, sir, for information sessions. I would also like to thank the organizing committee for giving me this opportunity. Thank you very much, sir.
Thank you. Thank you all.
Right. Okay, the next session is going to start after the lunch break. Thank you all the participants.